Hello friends, I welcome you all to this session on power plant engineering. So in the last lecture, we have tried to solve ideal Rankine cycle. But now in today's lecture, we will be solving a real Rankine cycle. Real in a sense, not exactly replicating a real power plant, but with uh, internal irreversibility. Now here internal irreversibility means the friction. So if there is a friction in turbine and pump, then what will happen? Entropy will increase and the state after expansion will be not this 2s but it will be this, that is this point. And the same thing will happen in the pump. So this will be your real uh, state after expansion and this is isentropic one. So let us take the same problem and use the same Excel add-in for steam tables to model it. So what we'll do is we will take this copy of this onto the Excel so that it becomes easy for us to view. So now this is my cycle and state 1 is the point where the steam enters the turbine. So it is entering at the boiler pressure. The temperature is the inlet temperature of steam and the enthalpy can be evaluated with respect to pressure and temperature for water. This is the pressure, this is the temperature. Then comes, now as this is basically the starting point, so we needn't have to find out for isentropic enthalpy because that will be required at 2s and 4s. So we will be directly jumping to entropy. So entropy based on pressure and temperature. This is pressure, this is temperature, that's it, done. Now comes 2, but we cannot move to 2 directly. Instead, we have to start from the 1 to 2s process only. So the entropy after isentropic expansion will be the same as the point 1. So this entropy, SS means isentropic and this HS means again isentropic. So here the entropy will be the same as this. Then once the entropy at this point is known, then I can tell what the enthalpy at this point is based on the entropy as well as the pressure. So what is the pressure at this? This is basically the condenser pressure. So pressure here will be this, and then the isentropic will be at enthalpy based on pressure and entropy for water. So this is pressure, this is entropy, and this is the isentropic enthalpy at point 2s. Now I want this to, how can this be evaluated? This can be evaluated with the help of efficiency of turbine. So let us look here. The efficiency of turbine will be equal to the actual work output, that is H1 minus H2, to that of the ideal work output, that is H1 minus H2S. So I know H1, I know H2S, I know efficiency of turbine. So H2 will be equal to H1 minus efficiency of turbine times H1 minus H2S. So we will be evaluating this. Okay. So the actual enthalpy at this point will be equal to enthalpy H1 minus efficiency of turbine times H1 minus H2S, that is, it is M7. So it is M7. Okay. Let us do what? Let us check it once more whether we have selected correct cells or not. Okay, we have done it. So you can see that the actual enthalpy at the point 2 is lower than the is higher than the isentropic enthalpy, that is the enthalpy we got after isentropic expansion. So H2S will be lesser than H, and this has to be because in real case we are not getting total work, we are not able to fetch total work output, due to which the enthalpy is retained with the steam at the end of expansion. Now once this is done, you can also evaluate the temperature based on pressure and actual enthalpy. So this is the pressure, and the actual enthalpy is basically this one, that is L, and this is 7. So this is close to 99.6, and this is nothing but the saturation value. Okay, and here if you want, you can also evaluate the entropy. So the actual entropy will be based on the pressure and the actual enthalpy we have evaluated. So this is the pressure, and the actual enthalpy is this one. So this is the entropy, and if you want the dryness fraction here to know whether this point is inside the dome or outside, so enthalpy based on pressure and dryness fraction based on pressure and enthalpy. So this is pressure, this one is enthalpy, and it is 0.947. It is inside the dome. Okay, done. What about 3? 3 is again at the boiler pressure. So where is the one? This is the one. Okay, done. Then your temperature at this point will be nothing but the 3 is the condenser pressure, so it should be this one. Then comes the temperature. So this is saturation temperature corresponding to the condenser pressure. Okay, now enthalpy at point number 3, it is basically the enthalpy of saturated liquid. So based on pressure, then comes the entropy. So it is entropy of saturated liquid based on pressure. So based on pressure for water, this is the one. Okay, done. Now point number 4. So we cannot evaluate it directly, we have to first evaluate 4s. So what is the pressure at 4s? It is the same as the boiler pressure. So this is the boiler pressure, and then the temperature I don't know. What I know is the isentropic entropy at this point, that is the entropy after isentropic compression at this point, should be same as point number 3. So what we are going to do, that we will keep them same. Once this is known, we will be evaluating the enthalpy at 4s. So this. So enthalpy based on pressure and entropy. So this is pressure and this is entropy. Once this is known, then we will be evaluating the enthalpy at point number 4. How to do it? Let us again head to the note. Now, the efficiency of pump is the ideal work required by the pump to that of the actual work. So what is required? H4 is required. So H4 is nothing but H3 plus H4s minus H3 divided by efficiency of pump. So H4 is equal to H3. So H4 is this, is equal to H3 plus it is H4s minus H3. So H4s minus H3 divided by the efficiency of pump. So now again you can see that the enthalpy at point number 4 is more than 4s. So 4 is slightly more than, this is more than 4s. Why? Reason being, because we have supplied more work because of friction there. And then comes the entropy. So the actual entropy will be evaluating based on pressure and enthalpy. So this is the one, this is the pressure, this is the enthalpy. Done. So now comes the temperature. You will be evaluating based on pressure and let's say enthalpy only. So this is the pressure, and what is the enthalpy? It is L9. Okay. So everything is now at the place. So now we know everything. Once this has been done, as I have copied it, so you can see the turbine work, it is H1 minus H2. Okay. The pump work, it is H3 minus H4. So it is H3 minus H4. The heat input will be H1 minus H4. So it is H1 minus H4, and the heat loss will be H2 minus H3. Okay, and once this has been done, you will be able to evaluate the network output, net heat interaction. They have to come equal, because in a cycle net heat interaction should be equal to net work done, and the efficiency of the cycle came out to be 30%. Now if you look this closely, previously it was 34% with the same data. Okay, but now because of the efficiency it has dropped. So one more thing you can also look from here. What is the impact of pump efficiency on the cycle efficiency? So if I reduce the pump efficiency from 90% to let's say 70%, so it is not reducing much. Okay, so let us keep it as 90% only. But what if I reduce the turbine efficiency from 90% to 70%? Now you look here, the efficiency part. So now it has dropped from 30% directly to 24%. And it should be, because the efficiency of the cycle is very strong function of the efficiency of turbine, because the turbine output is more. Okay, so this thing should be clear by this particular small analysis. Now if you want to draw the cycle, let us copy this. Let us bring it here. Oops. Here. Okay, now so if you try to find it out, that let us do what, let us see. Okay, so what we'll do is, again we will be plotting each and everything so that you can get the point again. Okay, now first thing first, we have to plot h1 minus h2. So add data. So x, so it is s1 s2, and then y-axis is t1 t2. Okay, then comes 2 3, so it is 2 3, and y-axis temperature 2 3. Okay, then what, then 3 4, then 3 4, then y-axis also 3 4. Okay, then comes 4 5, add. So this is 4 and this is 5, and then comes the temperature 4 and 5. Okay, then add, then 5 6, so it is 5, and then 6, then y-axis, this is temperature 5 6, and then finally 6 and 1. So it is 6 and 1, and y-axis it is temperature 6 and 1. Once this has been done, I hope I have done everything correct. So this is your cycle. Now you can see that this is not at all vertical, this is slightly towards right. Okay, and with the efficiency you can also play. So if the efficiency becomes 100%, so it becomes vertical for both. Okay, you cannot see the work input of pump because this is very small, but you can view it from here. What is the impact of efficiency? You can also see that line. So if it is 90, so it is moving away. So if it is, let's say, 80, it is moving further. So in this way the cycle looks like, and at the same time that is how we can solve for the real Rankine cycle. So this is no more an ideal, so this is real, that means with internal efficiency into consideration. So friends, in this way we can solve for the real Rankine cycle, that means the cycle in which the efficiencies of pump and turbine are taken into consideration. So in this lecture, till this point only, thank you very much for watching it.